Good day, students. Today we shall look into the topic superconductivity and the Bcs theory behind superconductivity, Meissner effect, isotope effect, the coherence length of electrons, and Josephson effect in superconductivity. So let me refresh, what do you mean by superconductivity? It is a phenomenon exhibited by certain metals when they are cooled to very low temperatures. So when they are cooled below its critical temperature or its transition temperature, it loses its resistance. That means it can conduct electrons without resistance. And that current is called supercurrent, and this phenomenon is called superconductivity. It was first identified by Camerling Owens in mercury metal. It had a critical temperature of 4.2 Kelvin. Now, let us look into the theory behind superconductivity. What is the reason for superconductivity? It was satisfactorily explained in the most successful way by Bcs theory. This theory has been most successful in explaining all the properties of superconductors, and it was developed by the scientists Bardeen, Cooper, and Schrieffer, and they received the Nobel Prize in Physics for developing this theory in 1972. According to this theory, the superconducting state of a metal is due to the cooperative behavior of the conduction electrons. Now, the cooperative behavior of conduction electrons means that there are a number of electrons that occupy the same quantum state. In this picture, we can see that in a sea of the positive lattice points, these blue points all represent the atoms or group of atoms in the lattice points, and the conduction electrons are free within this lattice to move around. Since it is a metal lattice, there are excess conduction electrons, they can move around. But when this metal is cooled, these lattice points, they do not have any thermal vibration, and hence they appear to remain stable in their positions. And this allows these electrons, conduction electrons, to flow through the lattice without any resistance or collision. Now, it is seen that these conduction electrons, they have a sort of interrelation among themselves, and that causes them to flow smoothly. That is, most of the electrons are seen to occupy the same quantum state. This actually is impossible. It is actually impossible because according to Pauli's exclusion principle, it says that no two electrons can have the same state of quantum states, right? And again, these electrons, they have a repulsive force among themselves, and they cannot come together due to these repulsive forces. But by overcoming these two clauses, these two principles, we can see conduction electrons flowing through the superconductors with mutual attraction. Here, the electrons attract each other in a certain energy range and form Cooper pairs. They behave like bosons within the superconductors, and these electrons, they attract each other through the distortion of a lattice point. Now, these electrons, when they move through the crystal lattice, so let us assume this electron, when it passes through this lattice, it attracts the nearby atoms in the lattice points and forms a distortion here, right? Now, when there is a lattice distortion, when it is displaced from its actual position, it will not be in a same position. It will sort of oscillate around its position. And this causes slow forced oscillations. Now, these slow oscillations of this lattice region, it causes the nearby electron to fall into that oscillation. In other words, these electrons get attracted towards this lattice distortion that is caused by the first electron. So, in the end, we can say that these two electrons are mutually attracted with each other. Now, these electrons, they move very fast, but the oscillations do not die out. That is why these electrons are attracted to each other. The attractive energy is able to overcome the mutual repulsion between these electrons only because that the lattice distortions, they go on oscillate for a longer period. Now the other electron passing through this distorted region, the second one, it experiences a force of attraction due to this oscillations. Now the electron repulsion is instantaneous, but attraction by means via a lattice distortion is highly retarded in time. That is, it is extended in time. And hence, this attraction via a weak lattice distortion can overcome the stronger Coulombic repulsion to form Cooper pairs of electrons. Now in this slide, let us try to visualize the formation of Cooper pairs. Here we have two electrons that are passing near a lattice point that is having a positively charged atom. Now these two electrons, they will experience mutual repulsion among them. The first electron, it sort of is attracted towards this positive lattice point. And this causes the lattice point to slightly distort from its position, moves away from its actual position. Now this distortion, it causes small, slow oscillations within the lattice. Lattice vibrations are caused, and these vibrations form another form of attraction for this second electron towards this region. Okay, now this in effect can be seen as a mutual relation between these two electrons, and hence overall we see the attraction between these two electrons, and they are called a Cooper pair. Now in this video we shall see this again. Electron is attracted towards the positive ion, and this causes the second ion to be pulled towards the positively distorted lattice. This in result forms a relation between these two electrons, right? Okay. Now, in BCS theory, let us try to see the electrons as wave vectors. Assume an electron is passing by with a wave vector k1. As it approaches a lattice point of a positive charge, it creates a phonon q and loses momentum. It is sort of being attracted towards it, and it will lose energy in the form of a lattice vibration. That lattice vibration is called a phonon. It is designated as small q here and loses its momentum. Now the phonon is represented as this lattice vibration wave here, and this electron then goes away with the wave vector k1 minus q. This phonon can be accepted by another electron passing nearby, which has a wave vector k2. Hence, The second electron then acquires this momentum during its interaction with the phonon Q and moves away with wave vector K2 plus Q. Hence, these two electrons are mutually related with each other by means of a phonon. Now, when the phonon energy exceeds the electron energy change, this interaction is attractive. If the phonon energy is greater than the electronic energy change, this interaction is attractive. Now, this interaction becomes the strongest when electrons have equal and opposite momentum and spins. Hence, we can define a Cooper pair as a pair of bound electrons having equal and opposite momenta and spins resulting from electron-phonon interaction. So, it is a pair of bound electrons that have equal and opposite momenta and spin, and they are formed due to this electron-phonon interaction. Here, the quantum of energy of the lattice vibration is called phonon. The lattice vibrations, they are quantized, and each quantum of energy of the lattice vibration is called a phonon. Meissner effect is exhibited in superconductors. So when a metallic superconductor is placed in an external magnetic field and that superconductor is cooled by pouring liquid nitrogen or liquid hydrogen over it, it reaches its critical temperature, and at that instant it will expel all the magnetic field lines from within it. Now this is a reversible process, that is, if I increase the temperature above critical temperature, then the magnetic field lines will be able to pass through that material. In another way, if I increase the external magnetic field up to the critical magnetic field Hc, again the magnetic field lines will be able to pass through it. So at Meissner effect, the field inside will be 0. Now this is because there is a reversible field produced inside the material, that is, surface screening currents are produced inside it, and it has an intensity of minus Ba. If the externally applied field is Ba, so there is a field developed inside of intensity minus Ba, and these two cancel out each other to form the field inside as B equals 0. Here H is the magnetizing field, that is the intensity of the external magnetizing field, and M is the intensity of magnetization, that is the extent up to which that material is magnetized. The flux density in the magnetic material, that is the number of magnetic flux lines that pass within that material, is B, and it is given as mu naught into H plus M. In the superconductor under Meissner effect, B will be 0, hence 0 equals mu naught into H plus M. This implies that mu naught cannot be 0, hence H plus M must be 0, that is H is equal to minus M. In other terms, the magnetic susceptibility chi is equal to M by H, this is equal to minus 1. Now if chi is having values from 0 to minus 1, it shows that that material is a diamagnet, but usually it has values of chi nearer to 0. Since here the chi value is minus 1, it shows a behavior of a perfect diamagnet and also a new type of diamagnetism. Now let us see what is isotope effect in superconductors. Now, the critical temperature Tc, the temperature at which we attain superconductivity, this varies with isotopic mass m, and it varies according to the relation Tc is proportional to 1 by root m. That means if the isotopic mass is larger, the critical temperature Tc will decrease or it will be lower. In the reverse way, if I say if the isotopic mass is smaller, the critical temperature will be higher. Now, the critical temperature is also related to theta d. Theta d is the Debye temperature of the phonon spectrum. Now, we see that when Cooper pairs flow through the lattice, there are lattice distortions in the material. These lattice distortions are called phonons, and when they are distorted, the material will exhibit a particular, the lattice distortions, they will have a particular temperature, and it is called the Debye temperature. Now we have the relation theta c is proportional to theta d, which is proportional to 1 by root m. And this shows that lattice vibrations are involved in superconductivity. Kindly note down all the points. What do you mean by the coherence length in Cooper pairs? The Cooper pairs are not affected by the lattice vibrations. That is, if the lattice vibrations have excess energy, that energy is not shared to the Cooper pairs. It is just that the lattice distortion is a medium of holding the two electrons together. That lattice distortion does not affect the transportation of this Cooper pair. Okay. Superconductivity is due to the mutual interaction and correlation of the behavior of the electron pairs. Okay, so these electron pairs, they do not attract each other directly. It is through a third person, through the phonon, right? So they are correlated among themselves. Their behaviors are related. Okay, so we say that the mutual interaction and the correlation of the behavior of the electron pairs, this will extend over a considerable distance, and it is this distance, maximum distance up to which the Cooper pairs are correlated to produce superconductivity is called the coherence length eta naught in superconductors. We can calculate it as eta naught is equal to h cut into mu f by 2 delta. It is obtained as 6.63 into 10 raised to minus 7 meters. So the distance between these two electrons in a Cooper pair is usually the order of 10 raised to minus 7 meter. Now the typical distance between two electrons, if they are placed nearby, is 1 attometer, right? In one atom, we can see electrons at either ends. So it will be in the range of 10 raised to minus 10 meters. But here, the coherence length eta naught is in the order of 10 raised to minus 7, far greater than that. This shows that the electron pairs, they overlap, they correlate with each other considerably. Now, let us look into the Josephson effect in superconductors. Now, if we sandwich a very thin insulator of the thickness of 1 to 5 nanometers between two superconductors, we get a Josephson junction. So in this figure, we can see that in between superconductor A and B, there is a very thin insulator C, and its thickness is of the range of 1 to 5 nanometers. This symbol represents a Josephson junction. The superconducting electrons, they flow from one superconductor to the other through the insulator. This current, it can flow continuously without resistance through this insulator without any external voltage, without supplying any battery, we can get current. And this phenomenon of the supercurrent is called Josephson effect. There are three types of Josephson effect: DC Josephson effect, AC Josephson effect, and the macroscopic quantum interference. Let us look into DC Josephson effect. Now, we say that if we just join two superconductors by means of a thin insulator, if we place a voltmeter across it, we will get the reading for a direct voltage. So a DC current crosses the insulator even without any external electric or magnetic field. This is because of quantum tunneling of electrons. So we obtain finite supercurrent at zero applied voltage. Without even applying voltage, we get the supercurrent across this junction. And this DC Josephson current produced, it is proportional to the sign of the Josephson phase. AC Josephson effect. Now, when DC voltage is applied across this junction, radio frequency RF current oscillations are produced across the junction. Hence, we can say that when a constant battery source is applied across this Josephson junction, we get AC oscillations, AC current oscillations across it. Now, the frequency of oscillation is given as F is equal to 2eV by h, where E is the charge of electron, V is the applied voltage, and h is the Planck's constant 6.626 into 10 raised to minus 34 joules second. And the third type of Josephson effect is macroscopic quantum interference. Here, if we apply DC magnetic field through a superconducting circuit having two junctions, the supercurrents formed, they show interference effects as a function of intensity of magnetic field. Here, it says that if I take a superconducting circuit and it has two junctions in that circuit, and if I pass a constant magnetic field through it, supercurrents will flow through this circuit. Supercurrents means the Cooper pairs are flowing through the circuit. And these Cooper pairs, they will have their own wavelengths. Okay. When these Cooper pairs, they flow, their wavelengths, they mutually superimpose among themselves, and certain wavelengths, they diminish and certain wavelengths are magnified among the Cooper pairs. And hence, we see an interference effect within the Cooper pairs. More number of Cooper pairs, they travel with particular wavelength, and more number of Cooper pairs, they lose a particular wavelength. Okay, so this is seen as the interference effect in supercurrents. And if I change the amplitude of this magnetic field, it will affect that interference effect also. This is used in sensitive magnetometers. Now let us look into the different types of superconductors. The first one is the type 1 or soft superconductors. They strictly follow Meissner effect. That is, if I take a plot of the magnetic field and the intensity of magnetization in that material, at zero electric field, this material is a superconductor. If I slowly increase the magnetic field, at lower magnetic fields, it is still a superconductor. But when it attains the critical magnetic field, it suddenly changes into a normal conductor. It loses its superconducting property. Okay. So this materials, they exhibit perfect diamagnetism below critical fields of approximately 0.1 Tesla. At other higher fields, we can see that superconductivity is destroyed. Since the critical field at which superconductivity is destroyed is very low, it has limited applications. And due to the same reason, they are called soft superconductors. The second type of superconductors are type 2 or hard superconductors. They do not follow the Meissner effect strictly. That is, at lower magnetic fields, they are superconductors, and by increasing the external magnetic field, it is seen that at a particular value of intensity of the magnetizing field, at Bc1 or Hc1, the superconductivity property is slowly destroyed. Only a few magnetic lines will be able to pass through it. Then if I keep on increasing the magnetizing field up to Bc2 or Hc2, we can see that all of the magnetic field lines are passing through it. The superconductor completely changes to a normal conductor. Okay, so from Bc1 to Bc2, we have a mixed phase. The magnetic field will only slowly penetrate the material at Hc1, and it completely penetrates the material at Hc2. Superconductivity is completely destroyed at very high critical fields of approximately 10 Tesla. And they are used to manufacture conducting wires to produce high magnetic fields. And due to these high critical fields, they are called hard superconductors. Now, superconductivity has applications in diverse areas. They can be used to fabricate high field magnets. They are used in NMR spectrometers and NMR imaging, that is diagnostic techniques. They are used for effective magnetic shielding. They are used for magnetic energy storage. They are used in SQUIDs and Josephson device. SQUIDs are an acronym for superconducting quantum interference devices. They are used in high-speed magnetic trains or maglev and in ships. And they are also used in computers and for information processing. That's all for today's session. Thank you.